Hello everybody and welcome to Keep Talking and Nobody Explodes modding. Today I would like to enhance the module that is right in front of you here called Ribbit Programming. Now this module was made some time ago by me and my friend Quinn. You can see here that the programming was done by me, the visuals and the sounds were done by Quinn, but that is a simplification. We were both involved. Like Quinn has helped me with the logic in the programming too. But one thing that this module doesn't have yet is Twitch Plays support. Well, that's not true. It has Twitch Plays support. A Twitch Plays autosolver is what I meant. So today I'm going to try to write such an autosolver for this module. So for this purpose, I've opened up the module in Unity. We can see it right here in the scene. If I do this, there you go. That is our module. So let me quickly show you how the module works. The basic idea is that on the start of the bomb, you see a not moving, a frozen version of the game game Frogger. This is an old arcade game. Those of you over the age of 50 might remember it. Some days I always want to add KTANE sounds. Okay, that is a terrible idea, Cyanics. Don't do that. So the idea in this module is that you are supposed to input ahead of time the movements of the frog that will take it to the end. Now I'm just going to press up a few times. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this will now cause the frog to just keep moving up. And if I now start it, you will notice that the frog will keep moving up. And then as soon as it hits that car, it dies, which means that at that point I might have gone left perhaps instead of up, or I might have waited for one frame. And then similarly, of course, here in the river, you have to be on the logs or on the turtles, and the frog moves with them. So if the turtles move left and the frog is on them, the frog moves left with it. And the goal then, of course, is to hit one of those three goal spaces here. If you hit the green stuff, you die. But it gives you like half a frog's width of leeway. So if you're like, if your frog is like here, for example, which is like almost half of a size of a space away from the goal, you can go up and it'll just jump into the space and it'll be fine. So that is the goal of the module. So our autosolver has to prepare the program correctly, just like an expert would. Poor frog. Yeah. Oh, thank you, Ghost Old. I do agree that Quinn has done some awesome work with the graphics on this module. Obviously, most of these graphics are directly from the original Frogger game, so, nostalgia 100%. 110 perhaps, even. Okay, so let's exit play mode here. And let's now take a look at the source code. So I'm going to double-click the script. How do you know which direction they move? If you mean the cars and the things, okay, so the turtles always go left, the logs always go right, and the cars show you which direction they go. So in this example, they would all go left. But, if I run this, you will see that they change. Right, so now we have those two go right and the lorry goes right, but this one here goes left. Right, and the speed at which they move, you get from the edge work. Right, but that part is not super important. Obviously, the autosolver will already know what their speeds is. In fact, let's take a look at the source code and see if we can find, there we go. We already have an array of speeds where the first 4 entries, I assume, relate to the bottom 4 lanes with the cars in them, and the remaining 4 relate to the logs and the turtles in the river. Now this here, I believe, gives me the sizes of the logs or the groups of turtles, and of course the cars, they all have a size of 1 except for the lorry. So we have an integer that tells us which lane the lorry is in. There is always exactly 1 lorry, and that one has the size 2. Okay, let's take a look at what you guys have to say. Good on you for calling it a lorry. One thing that will help me a lot is that this module already has code in it to check whether the frog dies. Right, there is a, let me find the Let me find the onInteract handler for the submit button, right? There is the submit button that doesn't seem to be called submit. We have, there we go, start cell. That is the KM selectable for the start button. And start press is going to start that process. As you can see here, it will start a coroutine called run. And this is where that coroutine is. So the program is running. While that is true, the buttons will just do nothing, right? So you can't run the program while it's already running. And you also can't stop it. You can't press reset while the program is running. Now, take a good look at what's going on here. Right, what we're doing here is we're iterating through each of the instructions in the program that the user has entered. Each instruction is either up, down, left, right, or stay. And this is identified by these enum values here. These are the 4 directions. And then, of course, we have idle to mean stay. And then each of these clauses here calculates what happens to the frog. So, for example, if you move up, then of course the Y position is subtracted by 10, right? You go up by 10 units. Maybe I should explain why 10, because everything in this module is in tenths of a unit. You will notice these little notches here at the top. This is how many units this is wide, that's 7 units. And the whole thing is, of course, 11 units tall because it's 4 plus 4 lanes, plus the patches of grass. But then each of these squares is itself subdivided into 10 by 10. Not so much the graphics are probably 16 by 16, but that doesn't matter. The point is that the speeds are all a multiple of a tenth of a unit, and therefore the position of the frog is always a tenth of a unit. So in the code, I represent them as subunits, right? So the frog Y position starts out at 100, right? Because since the whole thing is 11 tall, that means that the top edge of the frog is at position 10. Right here at the top it would be 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But then because I'm doing subunits, I'm putting 100. So in each case, there are things that can cause you to die. For example, you can die because you move up from the top row, or move right from the rightmost column, which you're not allowed to do, or move off the bottom, move off the left, or you died of boredom, right? The rules say that you can't have more than 5 idles in a row, or in fact you can't even have 5, so you can't have more than 4. You can only idle 4 instructions in a row. So, if at the end of this, after executing this entire program consisting all of these instructions, the frog is in one of these places. Okay, so here it says you died because you hit one of the barriers on the top row. So if the Y position is 0, then it means that you did reach the top row. And then these are the ranges in which it will allow you to be in order to count as no more than half a frog's width away from a goal. All right. The lane that the frog is currently in. This is an interesting calculation. Okay, so if frog Y is equal to 0 or 50 or 100, so if it's 0, then it's in the top row, and we've already dealt with that case. If it's at 50, then it's the patch of grass in the middle of the screen, and 100, of course, is the patch of grass at the bottom of the screen. And in those cases, we don't need to worry about hitting any cars or drowning in the lake. So we're just setting this to null for now. In all other cases, this is calculating the actual lane that the frog is in, where the bottom 4 lanes are 0, 1, 2, 3, and then the river lanes are 4, 5, 6, and 7. Okay. Now, if we are indeed in a lane, okay, so, this is interesting. Okay, so time is the amount of time that has elapsed since we pressed the start button, right? And we're doing modulo 1 to find out what fraction of a time unit we're in. So I'm going to call the seconds for now, although I don't know if it is actually seconds, but let's just say that it is exactly a second per command in the program. So what this will say is, it might say, for example, 0.5 if we're exactly halfway into a second. So if we are like a fraction into a second, we need to calculate our x position in the event that we're on a log or a turtle, because the log or the turtle will move us according to its own speed, right? So this will tell us the speed at which we're moving. We multiply that with the fraction of a second that we're moving, and we add that to our x position. Okay, now this, if you've paid attention, will actually give you a floating point value, because the time is a floating point value. In our autosolver, well, I'm getting ahead of myself, so let's look some more. So we update the x position of the frog, and then we need to figure out whether the frog can still live. There are three possibilities. Either the frog gets hit by a car and is roadkill, or it drowns in the river, or it survives. So if it's either roadkill or it drowned, then of course we need to we need to set the sprite to the skull thing, and then end the program and say that the frog is dead. Right, but if we survive this, then we also need to make sure that the program doesn't stop, you need to get the frog all the way to the top. So if our time has reached the end of the program and the frog is not in the top row, well, then the program ended before the frog reached the goal, so you're also dead. Right, in all other cases, we have solved the module. We update the frog position to align with one of the goals in the patch of grass on the top, and then we say handle pass. How does stuff like death result or roadkill work? Is it like a C# class? No, it's an enum type, right? So death result is simply an enum type. It looks like this. Is kind of like an integer, except that I'm giving the values names. So internally, this has the value 0, as you can see. Roadkill is 1 and drown is 2, but you don't need to worry about these numbers because we refer to them by the names. Okay? And here, by the way, is the function that returns that result. So we're given a time, we're given the x position of a frog and the frog, the lane that the frog is in. And then let's see what item x is. So item, I assume, is the item in the lane, which is either the car or the log. Right? The starting position of that car or log is in starting positions, and then we add the amount of time that has elapsed times its speed. And then we need to take that modulo, 70, because the whole thing is 7 units wide and we're doing tenths of a subunit, so that's why modulo 70. And we're doing this shenanigan here because the speed can be negative if the object goes to the left. So if this whole thing here is negative, then taking it modulo 70 would still be negative. And so I add 70 and then modulo it again to make sure that it is positive. So this will give me the genuine left edge of where the object is. Now the width is easy to calculate. If it's the lorry, then the width is 2 units, which is 20 subunits. Any other car in the first 4 lanes is 10 units. And everything else, of course, we have in our river sizes array. Okay, so if our lane is one of the first 4, which means the car lane, then we are roadkill if and only if our frog is hit by a car. Okay, so this condition here will simply check whether any part of the frog intersects with any part of the item. And then similarly, we do the reverse here with the drown, right? You have to intersect with some part of the log or the turtle in order to still be on it, right? This means that you can hang off of the ledge of it and you'll still be fine. But if you don't, you will drown. In all other cases, you survive. This frog die is my least favorite. I'm sorry, Guru. Making an autosolver for this seems like a Leviathan task. Well, hopefully I can convince you that it's not going to be that hard. So I'm actually gonna start right away. Except I am going to turn this loop into a function. Right, I want there to be a function which I can simply give a program, which is a series of up, down, left, right, and idle instructions, and it will tell me the outcome. It will tell me whether I'm roadkill, or I drown, or I hit the barriers on the top, or I succeed. Well, in fact, I don't even need to distinguish between roadkill, between the different types of death. I only need to make sure that that I reach the goal at the top. So, what is this mix variable? Let's see where that is used. So this while true, okay, so let me explain, because this is a coroutine, which means that it runs for some amount of time, right? During this while loop, you will notice that at the end of the while loop, we have a yield return null here, which means continue the game for one more frame and then do this while loop again. And so you will notice that it runs through the frog program, or the program, every single frame. Right, so for every frame, it tries to determine whether the frog is dead. And you will notice that it will only go into as many instructions as the current time is, which, so here's our answer, by the way. Apparently every instruction is 1.4 seconds. No, it's the other way around. It's 1 over 1.4, isn't it? Yes. So 1.4 seconds, okay, so it's 0.7 seconds per instruction, or 1.4 instructions per actual second. So what I'm going to copy into this new method is I'm just going to take this whole for loop, right, that executes the entire program, plus this part, which checks whether you reach a goal at the top, plus whether you've been hit by a car or a river at this time. And then we also need to check this condition here. So it seems that we need to check quite a few conditions. So I'm going to put this in my clipboard, and I'm going to say var result equals check program. And then I'm going to generate a method. Now, inside of check program, I probably need some things. So first of all, I need the time at which I want the frog's condition checked. Right, this mix thing. So what is a good name for mix? Mix is basically the instruction index that I see. Okay, so the point in mix is that at every frame we need to check whether we have just executed a new instruction compared to the previous frame, and if so, we need to move the frog, we need to play the sound when a frog moves, and do all that stuff. So that is not going to be part of the autosolver. So I'm going to do that differently. So what does our check program thing actually need to return? Right? Check program result. Let's see what kind of information we need to know about the result of this check. So the mix thing I'm going to deal with by saying that maybe we need to set the frog to a new set of angles. So that would be a vector 3, but because it might not be the case, I'm going to make that nullable by adding this question mark, new frog rotation. And then play frog move sound is implied by that, because every time that this gets set, we also play the frog move sound. But then we also need to change the actual frog position, which I've lost track of where that happens. So let me quickly check where frog is accessed. Set X, aha. Okay, so that happens inside of setup sprites, and setup sprites is called, okay, obviously setup sprite 0 at the start of the module, but it is also called, bingo, it is called here. And here. Okay, perfect. Okay. So we need to know the final position of the the final X and Y position of the frog. Yeah, and we need to know whether the frog is still alive after all of this. All right. In fact, yeah, no, instead of this, I think I want the, what did I call it? The enum that I just talked about, which has roadkill and so, you know what, I should just control a death result. Okay, it's called death result. Okay, so check program result, there you go. Let's call that the death result. Which means that for the purpose of the autosolver, I also need things like hit right edge, hit bottom edge, hit left edge, and hit top edge. Which actually I should probably do this in this order. Okay, and then in addition to survive, I guess we also want a solve. No, actually I think solve should be a separate boolean. Because it's not really a death result. Right, so this just means there is no death. Everything else is a type of death. Oh, of course, boredom is also a reason for death. Our method here, check program. So let's see. So if frog y is equal to 0, then we died because we moved up from the top row. So we want to return a new check program result. Now let me think whether I ever need the, yeah, I do need the X and Y position because I need to set up the sprite. Yes. So we don't need a new frog rotation, but I'm going to set frog X, and then frog Y equals frog Y, and then death result equals top, that one, hit top edge. Now frog X is a float, of course, I should have realized that. So these are actually floats. Okay, so this I now need to move to up here if result is not equal to null, and it has, whoops, oh, it's not a nullable, is it? Oh, of course. Okay. It's the vector here inside of it that is nullable, but not the check program result itself. So if we have a death result of hit top edge, then we need to do this. You died because you moved up from the top row. Okay, and we're going to do this for all 4 of the other edges. So I'm going to do that here. We return, okay, I'm just going to copy and paste this now. So here we have the left edge. So else if result.death result is equal to, I've already forgotten which edge it was, top edge, that one, then we do this. Now, I think this might potentially be more readable as a switch statement, so I'm going to do that. This should have been right edge, okay. Okay, so that was for the top and the right edge. Now let's do the bottom edge, which is this one here. So let's copy that here and say this is the bottom edge. So now if case bottom edge, then this. And then finally for this one here is for the left edge. So again, we copy this and say left edge and put that here. Case left edge colon that. Okay. Now, the next thing I need to take care of is these things here, right? So if, so this mix thing needs to be passed in. So let me see where mix is even updated. Because all of this only... I see. Yes, okay. So mix is a bad name for this variable. So let's see if we can come up with a new, most recently executed instruction. Let's call it that. Okay, and then here we have a most recent instruction. Let's call it that. And then I'm just going to use this inline thing to rename that. Okay. Now, in this case here, yeah, why didn't it? Oh, I see. Okay, yeah, I should just use the rename function. There you go. That is much easier. Okay, so what this will do is it will update this variable here. Yeah, I think, okay, so that means that in all of these examples here, okay, so the fact that I'm having this many like copies of this, I think I should just have a single instance of this. I should just have the var result equals new check program result. And then I should update this as I go along. And in particular, I should use its frog x and frog y variables directly like this. And then all occurrences of frog x and frog y in here. Frog x should be result.frog x in the selection, yep, and then frog y in the selection. Okay. Okay. Inside of the function, the frog x and frog y were always integers, which is why it's complaining about this here. No, that's not why it's complaining. This is the number, right, this is complaint, yes. Here I need an integer value, and I want to keep it an integer value. So I think I'm going to undo that. Okay, it's always good to have tried things and to have figured out, oh, interesting, the x is a float, but the y is an integer. Yeah, because we only need frog y to determine what lane you're in, whereas frog x needs to be fractional in order to determine if it is hit by a car. Oh, this is so fascinating. You know what? I'm going to redo all of this, and I'm just going to change this to int, because frog y is always going to be an integer. And now I think it will work. Okay, so if this is the case, then I'm going to say result.dethResult is equal to this. And then return result. There you go. And then we do the same thing in all of them. So here, this is left edge. Here, it is bottom edge. And here, it is left edge. There we go. So now the frog x and frog y are in the correct place. Now this most recent instruction thing, of course, I'm going to do the same thing with that. This is going to equal that. And then all occurrences of this in the rest of this function, right, I need to replace with this. So let's select all of this text. And then replace this with that in the selection. There you go. Okay. Now, I think I'm going to put a new line here because these lines are going to get a bit long. Right, and then I'm going to change this to say result.frog rotation. I'm going to change this to frog angle, because then I only need the y coordinate in that. So this would be 0. Yeah, okay, let's go here. Let's change that to new frog angle and have that actually be an integer. There you go. Okay, and then the play frog move sound is going to be done outside of this function. So I'm going to put this in my clipboard and then change this to result.newFrog angle equals, what was it? It was 90. Right, and then here it'll be 180, whoops. And then here it'll be 270. And then up here, where I call check program, I need to check if result.angle is not equal to null, then do both of these things, which means to set the correct angle of the sprite on the module, set that to new frog angle.value, and then also play the frog move sound. This, I guess I can update now. There you go. And I should probably do the same thing here, except the frog is now dead. Okay, so far so good. Now let's look at the rest of check program. What have you guys to say? You have two hit left edges, one at move left and one of move right. I see. Let's see. Top, right, bottom, left. These are correct. Top, right, bottom, left. So maybe you meant these here. Top, right. Thank you. Yes, that was correct. I am so glad that you found that. Congratulations and thank you. Okay. Right. Okay. Right. So here is the idle thing. So this needs to check. Oh, I completely forgot. So we're accessing underscore program here, which is of course the program that the user entered. But when we run the autosolver, we need this check program function to work with a program, a hypothetical program that we supply. So we cannot use the field. We need to pass in a new list of move called the program. I'm going to call it underscore program and then use the rename function. And then when I call check program up here I can pass in the actual program. I should probably do this. This is mix, right? And then mix is equal to result.most recently executed instruction. Yes. So, which means that, you know, I can rename this now that I know what it does. I should probably give that a proper name. Okay. So let's see what else is wrong in this check program function. Right, so after an idle, so we cannot say go to dead, but we're going to say result.death result is equal to boredom, right? And then we return the result. And then we need to check that here. So case boredom colon that. Okay, so we have now checked all of the death conditions that could happen during execution of the program. But of course, we might eventually be hit by a car. So we need to check that. So you died because you hit one of the barriers on the top row. Okay, so here we need to say death result. I don't think we have a value for that yet, do we? No, we don't. So let's do that. Hit barrier. Let's call it that. So we hit a barrier, and then we return that result. Case barrier. Do that. So now we look what lane we're in. Find out the fractional time unit. If that is here. Okay, so why can we not update? I cannot use local variable before it's declared. Well, I guess there is no declaration. Oh, there we go, var result. Okay, I'm going to have to call this. I'm going to not change this, but I'm going to call this D for death result. There you go. And then this is what we want. This is result.frogx. If that is the case, okay. So, okay, so frog lane, right? We probably want to communicate frog lane through the result thing here. So public int frog lane. I'm going to put a question mark there just because the variable in here is a nullable integer, namely this one here. So let's say frog lane, there we go. And then all occurrences of that we can just replace. There we go. And then we will put all of this. No, actually not this. So if this is the case, then result.death result equals dResult, and then return result. And then this stuff here needs to happen up here. Up here. There you go. So case roadkill that, go to dead, and then case drown, go to dead. Okay. This frog doesn't deserve this. You guys have an amazing empathy for the little pixelated frog from a 70s arcade game. Maybe you've watched Wreck-It Ralph too much, in which all of these arcade game characters are depicted as sentient people. So let's see. If time is greater or equal to program count, this means that we have successfully executed the program. If we are not at the top row, then the program ended before the frog reached a goal. We don't have a death result value for that either, so let's quickly add that. Program ran out. So let's go back here. That should be program ran out. Return result. And then up here, we're gonna say case that. I meant case ran out. Okay, colon, do this. Thank you. Okay. So far, so good. Yeah. All of that seems to, it looks good to me, rather. So this adjusts the frog X position in the case where it hits a thing. And then this, we need to put up on the top. So here we're going to say return results. So here we're going to say, do we have a Boolean for solved? I guess not. So I'm going to introduce one. Public bool solved. Right, and then this equals true. Right, and then we can just return results here. You know, because solved will just not be true there. And we still want to update the frog X. I mean, we want to return the value of frog X that came out of the rest here. So we're just going to return results here. Okay, so far so good. So after all of these checks here, we now know that the frog is still alive. So we need to do this, don't we? So if result.solved and the module isn't already solved, then we do all of this. Yeah, you know what? I'm going to put that at the bottom where it was. Okay, this is the bottom. Okay, so I think we're done making that a separate function. Now, we have a function that we can make use of, right? This function here, check program, that we can make use of in the autosolver. So let's see if we can do that. Now, I can never fully remember the name of the function that we need. Is it called Twitch handle forced solve? I think this is the correct name. I'm quickly going to check the wiki. No, that is not the correct page. This is the correct page. And indeed, I got it right. That is what it's called. Isn't it great when you can look stuff up on the internet? Haha. So, first of all, if the module is already solved, then we don't need to do anything. Secondly, so here's a little corner case. It is possible that the user is currently running a program already. So while something is there, program running. We're just gonna wait for that program to finish. If at that point then the module is solved, then we don't need to do anything. However, it is possible for this program to strike. And if you run an autosolver, then we don't want that to happen. In fact, let me handle strike. Where do I actually... Oh, of course I do that here in dead. Yeah, okay, that's fine. So I'm going to introduce a new Boolean to tell the coroutine that the autosolver is running. Autosolved, let's call it that. TP autosolved, to be a bit clearer. And then here in our, this one here, I'm only going to do this if the autosolver is not running. So this way I can guarantee that that this function will not strike. But it could solve, obviously, so we still need to check if the module is solved, in which case we don't need to do anything. Now, there is another special case, which is, imagine the user ran the program and then died, and then ran the autosolver, right? Because here's what happens. Let me quickly show you this. It only just occurred to me that this will now test run the changes that I've just made. But let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's run this. Okay, and now it's dead. Okay, so we did get an actual strike. But what I wanted to show you is that the module sort of remains in this frozen mode, and these arrow keys now don't do anything. And even the submit button doesn't do anything. And the only thing you can do is reset. And that will put everything back to what it was. So if the game is in that kind of state, we need the autosolver to press the reset button. Now, how do we know if we're in that state? We are in that state if frog is dead is true. So if the frog is dead, then we need to press the reset button. I forgot what it's called. Reset cell, that's what it's called. And then we wait for 1/10 of a second, because that's tradition after every button press, so that, you know, 1/10 of a second is still very, very fast, but, you know, at least it doesn't all happen like, you know, instantly, and you can't really see what's going on. So TP autosolver still look like someone is solving it, but very, very quickly. Okay, so we now have our autosolver to write. So we don't even need to care what the initial state of the module is, because we have our check program function, right? So all we need to do is just go through sequences of commands and then run those sequences of commands through that check program function. Okay, so for example, if I have a hypothetical program that is a list of moves that go like, I don't know, up and then maybe idle and then up or whatever, right? Then I can just say check program of my hypothetical program, give it a time. It just occurred to me that we don't actually want to limit it to a certain time, do we? No, we really don't. No, yes, actually we do. Yes, actually we do, because we need a partial program to tell us... Yeah, exactly. So we can't have the frog die from the program running out. But there's also another snack that I will come back to later. Okay, so check program is what we're going to use for that. Now, how do we decide on a hypothetical program? Obviously, we can't just go through all possible programs, because there are 5 instructions and a program can be up to 20 instructions long. So that would give you 5 to the power of, you know, that would be 95 quadrillion possible programs. We cannot possibly do that. So what we're going to have to do is we're going to have to try programs of a single instruction and then see which ones of these are still alive after one time unit, or rather after the instruction is executed. And And then, we need to add commands as we go. At each point, we're going to keep track of all the valid programs up to this point, but it'll be filtering itself to the programs that have died, or where the frog has died. What if the user has already input some moves but not run it? Thank you. That is a very good point. If frog is dead or program dot count is greater than 0. Because, if you enter some commands, let me just actually check if my claim is correct before I say it, because, okay, so if I enter some commands here and then I press R, it will literally just erase the program. So I can have the autosolver do that. So pressing this will, now that I think about it, maybe we don't even need this condition, because resetting on an empty program is fine too. So let's just always press it. Okay. So how are we going to do this? So there are fundamentally two ways that I can think of. And if Quinn is in the chat right now, he probably knows one of them. What do you mean by meh? Oh, you want me to keep the if condition, even though, okay, fine. You know what, you are right. It's a bit more elegant that way. Okay, let's think about this. So I don't know if Quinn is currently in the chat. Probably not. He probably would have said something, and he would probably be in the list. So many autosolvers that Quinn and I have written rely on an algorithm known as breadth first search, which is a special case of Dijkstra's algorithm. This algorithm basically tries all possible moves that you can make, puts them in a queue, and then every time that a move is invalid, it gets filtered out of the queue. And then at the end, you will eventually reach a goal position which is valid, and then you have the entire path that you need to the solution. So I'm going to implement that same algorithm again, simply because it's familiar. So we're going to need a queue. And that queue is going to need some item in it. And I claim that I only need the string that is actually the program, right? A string that contains the up, down, left, right, and idle characters. So I will easily be able to turn that string into a list of moves. Right, and then another thing that we need is we need to know which programs we've already tried out or visited, as the algorithm usually calls it. Right, now for every program, we want to know... Yeah, actually, I don't need this to be a dictionary. Right, I only need to know which programs I've already visited. Right, and then there will be a solution program, perhaps. Right, so, oh yeah, I forgot that we need to enqueue the empty program, which is the state at the beginning of the program, at the beginning of the module, rather. And then while there is anything in the queue, we are going to dequeue an item. So this will be a string. So this is a program string. And then the actual program is going to be, well, I'm going to select from this string, right? And now if that character is up, we're going to go move up, else down, else left, else right, and then in all other cases just use idle, and then make that a list, right? And then we can check this program. However, we don't want to check this program if we've already checked it before. So if we've already visited this this program string, then literally just continue with the next item in the queue. So this is how we filter it out of the queue, by just dequeuing it and then ignoring it if we've already seen it before. Okay. Now, I don't think I want to check the program here, because I'm probably going to check it after, like before I put it into the queue, right? So I'm going to check every possible program that can come after this. So for each next character in up, down, left, right, or idle, I'm going to add, oh, you know what, I should do this. So the moves that we can do are up, down, left, and right. Now we can add that move to the program, and then of course, after we're done, right, we're gonna do stuff here, and then after we're done, we're going to have to remove it again. There you go. And now we need to check whether this program is valid. So result equals check program. So the program that we want to put in is program. The time at which we want to stop this is actually program.count, right? If you have one instruction, then you only want to check. No, actually, so if one, yeah, you want count plus one, don't you? Because, okay, so if you have no instructions at all, then the program will actually run for one time unit. If you have one instruction, then it will run for one time unit, then execute the instruction, and then run for another time unit. And during that time unit, like if your first instruction is up and you're now on the street, then it could be during that second time unit that you get hit by a car, right? So that's why we need to run it for a little bit longer. And then finally, most recent instruction, we don't actually care about this. So I'm actually going to make that parameter nullable, like this. And then let's see where this is used. Oh. Yeah. Okay, so let's actually make this nullable as well. No, I don't want this nullable because I want this thing here to be able to just update that variable. So I'm gonna undo that. So here's what I'm actually going to do is I'm just going to pass in -1, and it's going to, you know, give me some value, and I don't care about that value. Right? It will also give me a frog rotation, and I don't care about that. I can just ignore those values. So that will give me a result. Now, the only programs that I'm interested in are the ones in which the result is either solve or survive. Right? If this is an actual solve, then we've found our program. So we can now break out of this. Well, actually not just break out of this for each loop, we want to break out of this entire while loop. So I'm going to put a label here, and then we go to found. Except that I need to remember what it was. So that is equal to, right. This can actually just be a list of moves, which is program. There you go. Yeah, I think this is good. Okay, so, you know, the fact that we have two variables for both the, yeah, I think I'm going to have just one variable here, and I'm going to make that a list. And then instead of creating a new list, I'm going to clear the list, and then I'm going to add range. Add range all of this. And then I will do all of this, and then I don't need this. I can just go to found, and then the program will contain what it needs to contain. I think that's fine. So if the result has a death result, then we don't care. So we only care if that is equal to survive. Then we need to put this new program into the queue. Right, so q.enqueue. And now we need to turn that program into a string again. So program, select, move. Now, remember how I said earlier that these enum values internally have integer values. So we have up is 0 and right is 1. So it would be up, right, down, left. And then idle is 4. So I can actually use the integer value of that move to index into the string, and then join that like that, and then that will give me a string representation of that program. Okay? So that should put all of the valid programs into the queue. And this should probably find a valid program. So if we ever get to this point, right, then we've exhausted all 95 quadrillion programs and none of them gave us the answer. So I'm going to throw an invalid operation exception here. It appears that this module is unsolvable, which it really shouldn't be, right? But you know, when we're done with this, we can actually run this algorithm, which finds a solving program at the start of the module, and then make sure that it is in fact solvable. I've never made sure that it is in fact solvable, that you don't run into a situation where there is a fast-moving car that will always run you over or something. So we can now write this part here. So once we have found the correct program, we can literally just execute it. So for each var move in program, for each move, right? If it's an up, then we're going to go move. Nope. What are these selections? Input cells is what it's called. I believe that input cells has the same indexes as the move enum. Right? It is also going to be in the order up, right, down, left, and C for idle. C because it's in the center of that D-pad. So I don't even need a switch statement here. I can just say input cells of int move dot on interact, and then you return wait. Okay. Then, after we've inputted that entire program, we now need to hit the start button. And then we need to wait for the program to solve itself. So while not module solved, yield return true. This should be it. Now, there is almost certainly a bug in this, because, you know, every time that you write this much code without ever running it, there is going to be a problem in it. So I'm going to run this, and it's probably going to throw me an exception, and then I can show you how we deal with these exceptions. Audio clip not found startup. Well, that is embarrassing. Why don't we put that audio clip? Yeah, let's put the lock icon there, and then put all of these things in here. There you go. And then unlock that. And now run this. Drum falls off a cliff. You hear that? Did you hear the module audio? Let me know in the chat. Okay, so. Yep, okay, cool. All right, let's see. 1, solve. Invalid operator. It appears that this module is unsolvable. Not a good omen. Let me just see if it always says that. Yep, it appears that this module is unsolvable. Okay, so that means that it couldn't find... Yeah, drum shatters into pieces. It couldn't find a valid program. So let's find out why that is the case. So here I'm going to debug.log format. I'm going to say examining program. I'm going to call this the program string. Right, new program string, there you go. Let's put that variable here and do that. And now I can tell it to output that. There you go. All right, now let's run this. Okay, so it has examined every program of one instruction. Well, except idle, I guess. It didn't actually do idle. But this one here is the... Oh. Yeah, no, that is the invalid operation exception that shouldn't happen. Okay, so that means that for this up command, it didn't find... Like, it claimed that the frog is already dead afterwards. So let's find out why the frog died. So here, program result dot death result. Okay, So I guess I can put this here now. Save that and run this again. Okay. Program ran out. Yeah, okay, that is a fair point. Okay. Hit bottom edge is grid. Okay, so the reason it fails is because it always says program run out, which is fair because, okay. Let me see here it goes less than the time. And the time that I specified is count plus 1, which is 2. So this for loop will run for 2 iterations. Yes, and during the second iteration, no, this does not have that. Yeah, it's here, isn't it? Where the program ran out. There it is. If time is greater or equal to program.count, then program ran out. Okay, we are okay with that. We don't care if the program ran out, because we know that the program is short. So if death result equals survive or death result equals program ran out. Okay, let's do this for now and run this once more. So even more than this exception that you saw, I'm actually more scared of an infinite loop. And I suspect that, that did not give, oh my gosh. Okay, it did enter a program, which was just you, and then it ran right into the lorry. Okay, so now we need to figure out why after a U. Yeah, so I guess I do want that output after all. It's unfortunate, now if I run the module, I will probably not get another convenient one where the lorry is right in front of your face. So I'm going to run a bomb with like 1, 2, 3, 4, 5, 6, 7 more copies of this, and therefore 8 in total. And then let's see this one here. This is likely gonna get hit by that car. Oh, here is one. This guy is on the truck. Okay, let's see what the speed of that truck is. Lorry, speed, oh my goodness, that has the maximum possible speed. Now, you can tell, right, this is 2 units, which is 20 subunits. If its speed is 26, it means that it will actually clear the frog before it will run it over. So, I'm gonna try this one here. This is number 5. Number 5, lane 1. Of course, they will all have speed 26 in the bottom lane. I didn't even think of that. So let's run a new bomb. Okay, so now the bottom lane has a speed of 10. This one will not hit the frog. This one will also exactly not hit the frog, but this one here will. So let's try this one. 4, solve, bang. And now we get an infinite loop, as I feared. Oh my gosh. Okay, so infinite loop is, let's die, let's hit the, yes, exactly. Okay, so how do I debug this, right? Okay, fine, I will use this to kill Unity. Where is it? There it is. Yes, terminate that. And then run it again. Okay, so in order to avoid such an infinite loop, so there are 2 possible courses of action that I can think of right now. One of them is to, just limit it so that it will only generate programs up to a certain length, like 5 commands or something, and then there won't be that many of them. In fact, there will be 3,000, which is reasonable. The other possibility is for me to transfer this code into a separate C# project where I can use the Visual Studio debugger. I'm going to try the former first, but if I get stumped by the problem, then I will use the latter, and then you can see me do that. So, if that is the case, or program string.length is greater than 5. Okay. So, the first lane has speed 7, so an up command should kill the frog. So let's do one solve. Okay, and we get lots and lots of results here. So when we go up, it says program ran out. Interesting, it says program ran out rather than frog got hit. That is, of course, problematic. Now, for left and right, this is fine, but for up, it should not say program ran out. It should say that you got hit by a... okay. So I know why this is happening. Okay, so here's why this is happening. I should not have closed that. I could have explained that on the... Okay, I will run it again and hopefully get some graphics that I can use to explain what's going on. Okay, bingo, we have this. Speed -1, this is extremely slow. This is 1/10 of a unit going left. Okay, so here's what will happen. After 1 unit of time, the frog will move up, and by that time the car will have moved left. And then 1 more unit of time will elapse, in which the car will still move. And during that time, during which the car can still move, it doesn't check whether the frog is on the car. It only checks it at the very end. And the reason it does that is because, you know, before I did the autosolver thing, I was running this coroutine which runs the program live, you know, in front of your eyes. And so it was going to get checked at every frame. And so it didn't matter because, you know, like it does the first command and then it will check simply because that is the time you're at. So let's try and figure out how we can fix this. And the way we need to fix this is that we need to check the validity of the program both after the last command and during the entire time interval that occurs after the command. So we need to check not just the program at this time, right? This time is the time after, like 1 entire time unit after the last command is executed. We need to check that the frog is still alive at every point during that. Okay, so between program.count and program.count plus 1. Time after time. Now, here comes a complication that I've been holding off of telling you about, but I think now might be the right time. Imagine this log here at the top of the screen. You will notice that it has a gap of only 2 spaces, right? So this log is of length 5. That means that the frog could be just here on the left edge of that log. And now imagine that log is all the way to the right of the screen. Now, if the frog is on the right edge of the screen, the frog will get pushed, like, you know, the edge of the screen keeps the frog in place, and then the log sort of moves away from under it, and that way it can drown. But now imagine this log is on the far right, and the frog is just on the edge of it, and the log is moving at a speed of more than 2. You will then realize that within a single time unit, this entire gap can move underneath the frog, and then the frog would land on the other side of the log before the time unit is over. And we cannot allow that to happen, because once you actually execute that, then of course it will check the intermediate frames during the animation, and then the frog will drown. So it's not enough to check only program.count and program.count plus 1. We need to check multiple time indexes in between. Now, I think, like I thought about this before coming online, I think that 1/4 of a time interval is enough. So I'm going to do that. I'm going to say that for var fractional time equals 0, fractional time less than 1, I suppose, and then plus equal 0.25f. Now I need that to be a float. There you go. Okay, and then I will check all of this here. Okay, so if at any point during this fractional time this tells us that it's solved, then we're good. But if it tells us that we're dead, so if death result is not equal to survive and not equal to time to program ran out, then go to busted. And busted is gonna go here. There you go. Okay, so if the program is not busted, like this, right, then we want the stringified version. I guess I'm gonna, just for the purpose of, no, I'm going to comment this out. And then we can enqueue this. Right, we can enqueue this program because we've checked the death results for all of them up here. Okay, so hopefully that will work correctly. I'm still not completely clear on, because I said less than 1. Maybe I need to make this less than or equal to 1, because once you, wait, hang on, no. Let's think about this. Let's say the goal strip, like the goal strip up here, let's say that one is actually down here and you only need to move up. Then your program will have length 1. Yeah, cancel that. Then your program will have length 1, and the amount of time elapsed will also be 1, because as soon as you go up, you've already won. There is no second time fraction. So I'm going to make it less than 1, because if the move solved it, then this will already say solved in the first instance where fractional time was 0. Oh, by the way, I forgot to add that here correctly. There you go. Yeah, so if the program solves it, then with fractional time 0, then this will already say solved. But if it's not solved at this point, then we need to make sure that the frog can survive another entire time unit, and we do that in steps of 0.25. Hopefully, this will succeed. So, what I expect to happen now is I expect to get that same exception that we said earlier, because I've just limited program length to 5. So this should go through all possible programs of length 5, and then eventually find that this much is unsolvable within 5 steps. So that makes sense. So let's remove that restriction again and run this. And hopefully now it will actually find the solution. Solve. Okay, we have an infinite loop again. That is what I feared. See, the problem is I don't know for certain whether this is actually infinite or whether it's just taking a very long time, because we're going through a large number of possible programs. Okay, it just occurred to me that yes, actually we are going through an extremely large number of possible programs, because for every time that we try to go up, we also try to go down and left and right, which means that this algorithm is now exploring all possible ways for the frog to go everywhere. Oh, there we go. Oh, look at that, look at that, look at that. Interesting that it went left, right, left. Oh, I see. I didn't actually allow idle as a possible instruction. Okay, so there we go. We now know that the algorithm works, except that it is like way under optimized, right? Because it is going through far too many possible programs. So we need to, whoops, that is not the window meant to open. Program count plus 0.5. Well, it could technically get infinitely long, but the theory is that if there is a solution, then it will eventually find the solution. And in fact, it will find the shortest program that will solve the module, right? Because it will never create longer programs before shorter programs, right? So it will only start exploring like 5-letter programs once it has gone through all 4-letter programs. Isn't that the monkey with a typewriter approach? It would be the monkey with a typewriter approach if you generated entire programs and tried them all out. But I'm trying them one instruction at a time, right? So if you die after going up after the first instruction, then it will not try any other programs that start with an up instruction, right? But still, okay, so this is still too slow, which is kind of understandable. So I'm going to restrict this to programs that have, in fact, I'm first going to run the program with no down instructions, right? Never allow the frog to go down. And if it cannot find a solution with that, then it will try with at most 1 down instruction. How about that? Okay. So first of all, let's make it possible to idle. Whoops. Okay. So let's go here. So for each allowed downs, so I'm going to start with 0 allowed downs. Well, and then I'm just going to keep incrementing that. There you go. Do all of this, and then do this. There you go. So now this will definitely be an infinite loop if the module is actually unsolvable. So maybe I should let's limit it to 20, I guess. It's never gonna reach. I mean, if it is solvable, it's solvable with at most 1 down, surely. Okay, so here we need to say if next move equals down and program.count m equals down is greater or equal to allowed downs, then continue. Okay, so we will not add down commands if we already have the allowed number of them. So I claim that this will run a lot faster, except at the moment it doesn't run because there is apparently, of course, the variable program, which is this one here, needs to be outside of this loop, and let's use a var there. Okay, so we clear this list here, we add the entire program here plus 1 extra command, and then if it finds that, we go to found, and then the variable program will contain the solving program here. Okay, so let's run that. Solve. Okay, it's still taking a while. Oh, it's still taking a long while. Okay, this is several seconds. That is still too slow. I'm very surprised by that. Oh, actually, I shouldn't be surprised because I've removed the possibility of down, but I've added the possibility of idle. So I should. So it is still doing stupid things, right? It's still going like left, right, left, right, left, right, which it also shouldn't do. How can I limit that? I suppose I can make it so that you can never go left and then right again. Because doing that is the same as 2 idles. Would that help? The problem is I mustn't restrict it. Oh. Should you perhaps filter e.g. LU versus UL where both programs finish with the same state? Yeah, I'm trying to think of like whether there is maybe a. Oh, of course. How about this? Once you've reached a certain, like once you've reached the middle strip, you never need to try any other programs. So why don't we just run this algorithm first, only up to the middle strip? Okay, so you're saying identical x, y, and time. Yeah, that's a very good point. I mean, that's still a lot, right? Because the entire board is 7 by 11, or rather 7 by 10 possible places. So that would be 7t times the number of time units. Yeah, actually, that's not that many. No, I think you have a very good point there. Yes, okay. So for those of you who couldn't follow that, what Bagels is suggesting, quite accurately, is that if you go up left, or if you go left up, then you're in exactly the same position at exactly the same time. And if both of those are survivable, then you don't care which one we do. We only need to explore one of those. So instead of having a hash set of strings here, I mean, okay, I'm still going to do strings, but instead of putting the program string in there, I should put a string in there that represents the frog position, and the length of the program, which is the same as time index. So, yeah, unfortunately the frog position, unfortunately the x position of the frog is a float. However, it should always be, a multiple of 1/10. So I guess I could just multiply it by 10 and then turn it into an integer. But the only reason I don't already do that is because, fractional frames. During the animation, you can have like any fractional amount of time. But at the actual sort of integer time intervals, like after 1 unit of time, 2 units of time, 3 units of time, etc., the frog's position is always a multiple of 1/10. So let's do that. But in order to do that, we actually need the queue to contain not just the program, but also the x, y, and time. Yes, let's do that. Okay, so we are going to have a struct. I'm going to call it a queue item, and I'm going to make it I-equatable. For those of you who don't know what that is, I'll explain that later. I'll explain that in a second. But first, let's see what information needs to be in the queue. Well, I'm going to put the entire program there. I'm going to put the frog x position, and then the frog y position, and the time is the same as the length of the program. So this is really all I need. Okay, now for this. You see, if you have two instances of this, we need to define what it means for those two instances to be the same, in other words, equal. So we are going to implement this equals function, which says that this queue item is the same as the other if the program is the same and frog x. Interesting that it doesn't autocomplete that. I was expecting it to autocomplete that. And then frog y, there you go, now it autocompletes that. Okay, and then while we're at it, we're also going to override the object equals function. Oh, apparently this allows me to use expression bodies now, cool. So this is the same if obj is in fact a queue item, and that queue item, well, that is equal to this, which is the same as saying ours is equal to that. And then finally, we need to override the get hashcode function, which tells the hash set what bucket to put these queue items into. And here I'm just going to use program.get hashcode times 47 plus frog x, and then do the whole thing times 47 plus frog y. And that should be good enough. Okay, this is not happy. Okay, that's not available in version 6. Okay, that's unfortunate. So we're gonna say if that is that, and whoops, that is a queue item. There you go. And that needs to be obj. Okay, so far so good. So now we can put things in our queue here, queue items. Right, and then the first thing that we enqueue is of course one where the program is empty. The frog x position is 30. I think it's I closed Unity. Yeah, so the whole field is 7 wide, and the middle of that is position 3 to 4. So the frog X position, which is the left edge of the frog, is at 3, which is 30 subunits. And then frog Y, of course, is 100. So that's our first queue item. So I'm enqueuing that item with the empty program. And then here, after I dequeue it, I need to check whether oh, now I see what bagels meant. Yes, okay. We don't actually want the frog X and frog Y in the queue item. We want it in the visited hash set. This one needs to have the program length and frog X and frog Y. So the question is similar moves. Yeah, okay. So I created this struct here, queue item, which would remember the program, the frog position, and the frog X position and Y position. But now I realize that I really want this hash set to... Yeah, so I guess I'm going to need another struct, don't I? So here's what bothers me, right? I could actually just dequeue only the program string, the instructions, and then run check program and have the result of that, which is the the check program result struct here. And then I can just use these variables because that will tell me where the frog is at the end of the program. But that would be one extra invocation of check program, and we're already checking it 4 times for every program. Yeah, I think in the interest of clean code, I think I'm going to do that actually. So we don't actually want queue item here. We want these to be strings. We want that to be the empty program. But we want our visited item to contain this. And then this is program length, which is the same as time. So let's call it time. Okay. So now we don't need to call get hashcode on that integer anymore. So I'm going to get that program string. I'm going to fill that list with these instructions, and then the initial result of checking the program at the time program.count with -1 there. So if visited.contains, so visited should now be a visited item hash thing. And if that contains an item where the time is equal to program.count and the frog X is equal to initial result.frog X and the frog Y equals initial result.frog Y. There we go. Now the frog X could be a float here. So I need to turn that into an integer after multiplying it by 10. I'm worried about rounding errors here, so I think I'm going to do this. I think that might be more reliable. So if visited already contains that, then we continue. Visited item. So we need to remember that. Oh, it just occurred to me that I never actually added things to visited. Well, that is okay, so we need to add that. There you go. Let's see if that works. Okay, so I need to reopen that scene again. I'm going to reopen Unity so that it remembers that I want that scene open, so I don't have to do that every time that I get an infinite loop. Okay, run that. And press solve. Okay, it did enter a relatively long program. Yeah, it did a lot of lefts, and then it died. It did a lot of lefts and rights at the start, didn't it? Here, entered program. It did left, left, and then 4 rights. So left, left, right, right should already not... No, it could happen because the time progresses. Yeah. Okay, but it didn't correctly determine that it would die at this point. Well, this is frustrating. Also, audio clip not found, right? Because I never saved this, did I? Let's put those audio clips back in. Okay, so let's save the scene and then reopen this. Yes, it's equal to 4 idles, exactly. Yes. No, they're exactly as, like, it's neither more nor less preferable. They're exactly equivalent. And I suppose it would do the left, left, right, right first, because left is first in this array, and then right, and then idle. If I were to move idle to earlier, then it would prefer the idle. And also, yes, left, left, right, right is funnier. Okay, now let's figure out why it died, even though... now I closed this, didn't I? Okay, so... I want to log every use of the function check program. But, you know, that would be a lot of data, so I don't think I want to log it into the Unity console. That would A, slow it down too much, and B, it would be too difficult to search. So I'm going to log this to a, what's it called? A text file is what it's called. So, in fact, since that is a type of debugging that I want to be able to undo later, I'm going to stage everything that I've written so far so that I can easily undo that. Maybe 0.25 isn't fine enough. No, I mean, if you can figure out why it might not be fine enough, then explain. But if you're just guessing, then no, because I thought about it, and the fastest that you can go, the fastest that anything can go is 2.6, and the largest gap, sorry, the smallest gap you can have between the start and the end of the log is 2, and the largest car you can have is 2, which is a lorry. And therefore, one time unit would allow you to skip over, but you know it should actually catch it if you only do like you know the middle of the time interval. But we're doing quarters. We're doing 4 times more verification than I think you need. Okay, the smallest gap is 2, but you're right, a car of 1. Okay, fine, you're correct that a car of size 1. But the thing is, in a quarter of a time unit, the most that a car can go is 0.65. Right, so if it didn't already, like if you didn't already run into the car when you entered the lane, then the car will hit you a quarter of a time second, a time instance later. Yes. So, okay, so here's what I'm going to do. I'm going to write file, write all text. So I'm doing this just to empty out the file, so that when I run it multiple times, I will have only the logging that I want. And then in check program, right, I'm going to, hang on. Unfortunately, there are lots and lots of calls to return here. Not calls to, but lots of return statements. But I guess I can do a try finally. Right, this will get executed no matter what. Right, and then if I declare the result outside of the try finally, then I can access the result inside of the finally block. So I'm going to append this text, which says check program, and then I'm going to I've done this before, haven't I? Here this thing here, this program.select. This will turn that into a string. Okay. And then I want to output, oh yeah, also the other parameters. The next parameter is the time. And then we have most recent instruction, which really shouldn't matter, but let's put it in. And then we're gonna go result. And whoops, for this, I'm going to add a toString method here, which hopefully, let's see, okay, so we want the frog X, frog Y, frog lane, let's say this if there is no lane, and then of course the death result, most recent executed instruction. I mostly don't care about that, so I'm gonna put that at the end. Solved. So if it is solved, then I'm gonna say S, otherwise U for unsolved. Or actually no, I think it'll be easier to search if I use something more unique for this. Solved or not solved. And then the new frog angle, I care about that one even less. So I'll just put that at the very end. Okay. Now, the thing that I care most about is the death result. So I'm going to put that at the front. But the death result, if it's solved, then we don't care about the death result. So I think this is what I want. So now let's run this. So this will probably create a relatively large file, which I can then Control F through. It seems to do some clever things already though, right? Oh wow. Hey! Okay, so that program was valid. Pretty cool. So I guess I need to, right. I need to run multiple modules, but then I want those to be separate files. So I'm going to add the module ID here. So module ID, that. Okay, and where do I clear it? Here, that. Okay, so now I can run any number of these and then look at the correct file for which one failed. And by the way, I can show you what this looks like already. You will see that this file is pretty large. It's 355,000 lines. Oh, I forgot to put a new line at the end. Okay, good thing I looked at this. Good thing I looked at this. So check program is here. Right, so at the end of this, I need new line. There you go. Recompile that. And then run this. So I guess I want to, oops, what did I press? Okay, I want to erase that now because it's not going to use that particular file name anymore because it appends the module ID now. Oh, I wanted to run multiple modules. Let's do that. 1, 2, 3, 4, 5, 6, 7. That makes 8. So it seems to work in most situations. Well, I don't want to run solve_bomb because, you know, I basically want it to stop when it goes wrong. So, bingo. So, I need to look at temp2.txt. All right, so here is all our programs, and as you can see, there are 4,711 invocations of check program. Right. So this died after I should have counted how many instructions were executed here. It must have been after the third. It must have been after LUU, because because the next instruction would have been another U, and then it would never have gone back down. So let's look for check program, open parenthesis, LUU, comma. Okay. So this is the time, isn't it? I really don't care about this value. Maybe I should have just not included that at all. So it says program ran out, which I suppose is true at this index, but not at, no. It ran into a car. That car should have hit it. So when we check this program at time 3, let's see, this is the frog position, right? That looks correct. Program ran out. Yeah, it jumped and then the car drove into it, exactly. So why doesn't it detect at this time? It doesn't detect that because the program runs out before that happens. Yes. So our check program function here, right? This does that. I need that to be less than or equal to. No, hang on. Yeah, no, that's right. So this goes through all of the instructions and executes the instruction. And then after it has executed the instruction, yeah, see, okay, right. Okay, so this bit here executes the time unit before the instruction, which means that it doesn't do anything after the last instruction. IP stands for instruction pointer. That is a very common term in assembly language programming. So if I did less than or equal to here, right, then obviously I need this to hang on, how does the other yeah, so after all of this, right, we check if we win, we check what lane we're in, and then we adjust our own, we adjust our own position, and then we check if the frog dies. This should work, right? Even for a fractional amount of time. Yeah, exactly. This is exactly what this was for, isn't it? That is the fractional amount of time. Yes. Okay, so the only problem is that no. It should still have returned here. It should still have been roadkill. Okay, so here's what I'm going to do is I'm going to make this logging even more extensive. I'm going to output yes, I'm going to output the the entire conditions, like the speeds of all the things and the starting positions and everything, and then I can run this through a debugger in a separate program. So that's what I'm going to do. So let's find where I append text. There you go. Let's put a new line here. Okay. So let's put some, I don't know, this. Wait a second. I don't need to log that with every line. I can just log that at the start of the file. Yeah, that's what I should do. Just put it here. Okay, so let's see. So the starting positions, let's join these with commas. So these are the starting positions. You know what? I'm going to write it like this because then I can literally just copy and paste it into the program that I'm going to debug. Okay, semicolon, new line. So that's a starting position. Then we want lorry lane equals lorry lane. New line. What else? We want the speeds, obviously. Dot join. Like that. Now, I believe that speeds is integers, isn't it? Yes, and this is also integers. Everything is integers. The starting position of the frog is always the same. I don't need to log that. So I think... Oh, wait, the directions that the cars are facing is in the speeds. Oh, that's right. We need the sizes of the logs and stuff. I can't remember what that was called. This dot sizes, river sizes is what I called it. Okay. And river sizes is a int array. Okay. Okay, I'm gonna put a new line. I'm gonna put 2 new lines here so we can see it. Okay. Now let's run this. And let's try the same thing again. So again with 8 modules. And again, I'm going to solve them one by one so that, you know, it stops when an error occurs. Okay, that worked. And that was also quite a clever solution. Number 2. That worked too. We need a case where it's, you know, only just about to be hit by a car. 4. What a maneuver. Bingo. Okay, number 5, top left corner. Bingo. Okay, now we have one. Number 5. So I can close this and I want to open temp 5. And here are, oh, I forgot the join there. Okay, I can fix this. The sizes are, is that 4 or 5? I think that's 5. That's 5, 3, 3, 2. Okay. Now I'm gonna keep Unity open. Well, in fact, no, I can just take a screenshot of this. This is all I need. There you go. I think I should probably zoom in a little so it's a bit more readable. Okay. So let's minimize this. Let's open my temp thing. And then, you know, while I'm at it, I should also fix this so that if I need this again, I will not forget. Okay, so I can delete the stuff that I've done yesterday. I won't need any of this. Curious onlookers can try to figure out what that does, but it's not particularly exciting. So we have all of this stuff here. There is a semicolon missing, I get it. So where's my other Visual Studio? It's right here. So let's put that missing semicolon there. And then get the function. The function is called check program. Here we go. So this entire function, along with the struct above it, let's copy all of that into here. There you go. Now, yeah, I also need the death result enum. So let's copy that as well. We need the move enum. Oh, come on. Thank you. That is what I wanted. There we go. And then I think we also need, okay, underscore speed. So I'm going to make that function a local function like this. Okay, and then I'm going to move it below this so that the variables are on top of it like this. Okay, now what I actually want to check, why doesn't it let me just do this? So the program I actually want to check is, let's see, good thing I took the screenshot because I forgot. Shit. Okay, I still have the logging here. We were looking at module number 5. So I need to find the program. Oh, right, it's down here where the autosolvers are. There you go. This is the program that we ran. And we died because we got hit in lane 3. Is that correct? 0, 1, 2, 3. That is indeed correct. 1, 2, 3. So I expect that this is the program. I hope that you guys concur. So the program should be that dot select for each character. We want I have it. Oh, right. Oh, right. No, I can just say, I can turn this into an integer, right? I can just find up, right, down, left, minus dot index of that character and then turn it into a move. And then that I can turn into a list. So the time apparently was 7. And that one I don't care. So var result equals that, output result to the console, and then break the debugger here. It seems to, its value is never used. Why would it never use lorry lane? Because does frog die uses it, and I haven't copied that. There we go, that function. We need that function. Yeah, let's put that function here, I guess. There you go. Okay, module ID. Right, I don't want that logging anymore. So I now have all of that. So if I run this now, it should now stop at the debugger break, which it does, and then we can look at the result in here. Right, and it says, it should say the same as this here. It says 2 and then 50, 70, and it says program ran out. Okay, so now I'm gonna run this with 7.25, and I expected this to tell me that it got run over by a vehicle, but it didn't. Okay, so we need to, what's the word, debug this. In fact, let me try something. The frog, right, at time, I can give it a time and an X position, which in this case is 50, isn't it? And the lane that it's in, and the lane would be 0, 1, 2, 3. Except this is the other meaning of lane, where this is 0, 1, 2, 3, and then these are 4, 5, 6. So this is actually a 2. So let's take a look at this and debug this. But in fact, maybe I should first check what it actually returns. So let's output that and debug break there. Okay, that gives me survive, which it shouldn't, right? I should have gotten hit by that car. So let's go here and find the X position of the car in that lane. It claims 26. Okay, so that's 2.6, right? Which is 0, 1, 2, 2.6. That's absolutely not what this is. Well, that is annoying. The speeds seem reasonable. Let's see if the starting positions match up. What I can't see what was on the module at the start. Oh, god damn it. Maybe I should have taken a screenshot of that as well. But I mean, there's no reason why that should be a discrepancy, because we output that here. These should be accurate, right? Even though it's kind of unusual for there to be so many zeros, but it's not impossible. I mean, it's only a number out of 7 possibilities. So, yeah, this could be right. So the frog lane is 2, and the lorry lane is 3. That is correct. 0, 1, 2, 3. Okay. So what is the starting position in the lane that we're looking at, which is lane 2? 0. Does that look reasonable? So what was the speed in that lane? Okay, 2.3. So at time 7, right, what was that? At time was 7.25, right? So at that time, whoops, yeah, it would have moved quite a lot. So let's modulate that by 17, and then it claims that it's that can't be right. So it claims, so what is the speed again? 23. So it claims that 2.75 times that is exactly, oh, wait, no, no, no. Okay. Okay, I had a knot in my brain right now, but I'm back on track. So, okay, so this algorithm thinks that the car is further left than it should be. Don't know what plot means. Oh, because I made that noise. Got it. So I think I need to try this again with a module where I have a screenshot of the initial position. So I need to do that. In fact, I'm tempted to even record. Yeah, let's actually do that. Let's actually record the solving process. So I'm going to zoom into this. I'm going to say 1 solve, but then before I run it, I'm going to do this and press video and then start. Finish. Okay, so now I have to constantly delete these because, you know, obviously I want one that fails. So, yeah, let's do this again. Video, start, and then to solve. Well, that's working as well. So we can erase that video as well. So let's go to number 3. Type 3 solve. Do this. Video. Start. It's very convenient sometimes how the logs are in the right place and everything. Okay, 4. If you threaten the program with the possibility of video evidence, you will scare it into always work. Yes, absolutely. Finish that. 5. Okay, I can't press that without, oh dear. If I press this now, then, oh god, I can't press enter in here. Okay, let's delete that file. Let's do video this, start. And it just works. Okay, this is gonna be even harder to, oh gosh. Okay, let's do this. Okay, video, start, and then do this. 6, solve. Enter. That also works. Number 7. You know, I've never been this eager to see something fail. Video. Let's see. 7, solve. Start. Bingo. Finish. Okay, now we have video evidence. Okay. And that was number 7. So let's write down this. Close this, open temp 7. That. Program is that. You died because... Okay, so now to do some lawyering. Okay. Oh, because of video evidence. Oh, I gotcha. Okay. So, these things all go here in my little program. Bang. And then I want to see if the frog dies at... Okay, so where did we die? We went 1, 2, 3 up. So it's probably here. I say probably, but I should probably check the video. One, 2, 3, 4, 5, 6, 7. Okay, so it's somewhere within the 7th time period. Yeah. So, I should be here. So I do want to check 7.25, but that one should still narrowly be fine because it was near the end of the interval that it died. Oh. No, that should still be fine. Okay. Well, let's figure this out. So, first of all, let's see what this outputs. Oh, wait. No, it's fine. I do want that. So this is now, oh, the frog position is wrong. Cancel that. The frog lane is, oops, no, I want the screenshot, which is here. Oh, I closed the video. Why did I close the video? Okay, so there you go. The lane is 2, so that's correct. 0, 1, 2, 3. Right, so the frog position should be 30. Okay. And it still says survive. Now, I think that is actually correct. Because if we look very closely, okay, let me actually count. So this is the start of time 0. 1, 2, 3, 4, 5, 6, 7. At the start of 7, it's still fine. And in fact, almost at the end of 7, it is still fine. So it should die at somewhere around 7.99. Roadkill. That works. Okay. So. I see. Okay, so now if I run this program with that time index, so this should say that it's fine. Let's do this. This actually says program ran out. This actually says program ran out. Okay. Right, but if I do literally anything after that and then ask it for 8, right, it should be roadkill now. It is roadkill. Right, but what if instead of you I make that a right, if I move the frog to the right? Program ran out. Okay, so now we've got our issue. Now we understand what's going on. So we're checking the time interval at like 7, 7.25, 7.5, and 7.75, and the car still doesn't hit the frog by that time, right? And then nowhere in the code does it check whether the frog is hit at time 8, which we need to check as well. Right, and I believed that this is checked at the start of the next command, but it isn't because it executes the next command. Right, so if the next command is right, then it'll just go right and escape the car. Whereas when the animation runs on the module, it does get hit by the car. May I ask a question? Wouldn't it be possible to check every step the program runs, I mean the VS program, to debug every possible step, and then one should find the culprit? I mean, that's kind of what I'm doing. I'm unless you mean the coroutine, in which case I would have to implement like a timing mechanism. But anyway, we have now found the problem. We need to make sure that the frog is still alive at the last time interval. So let me go back here. Okay, so program.count. Right. Here, where we add these fractional times, right? I specifically put less than 1 here so that okay, so our time index was 7. So this would check 7.25, 7.5, and 7.75. If I change this to less than or equal to 1, then it will check 8 as well, but then it will say that the program ran out at 8. It will not say that the car hit the frog. So maybe we should fix that, right? Maybe that if I actually put 8 in here, and this is 1, 2, 3, 4, 5, 6, 7, 8, yep. So we've determined that this says program ran out. We need to make it say no, roadkill. We need to make it check that the frog doesn't intersect with a car at the time 8. How do we do that? We do that by checking before. Yeah, why doesn't it do this, right? If the frog is in a lane, which it is, we adjust its X position, and then we ask if the frog dies. Right, this is because okay, I now have 2 copies of the code. I need to make sure that I know which copy of the code I'm in. Okay, so the issue is that in our okay, you know what? I'm gonna go here in here. There you go, and then I'm gonna look at this here. Okay, so in our program here, right, we have 1, 2, 3, 4, 5, 6, 7 instructions. All right, as long as I feed it those 7 instructions, this for loop will run only 7 times, even if the time is greater than 8 or 8. But if I give it an additional instruction, which in this case is right, then it will actually move the frog to the right at the start of the next instruction before checking whether the frog gets hit by a car. So I think I want to call does frog die inside of this loop. Do I? Yes, I think so. So if, okay, so var premature death equals does frog die at the time, which is, I don't even have a time, do I? I suppose I have IP. Yes, I do want IP, don't I? And then the frog x is result.frogx. And the frog lane is what I literally just determined. Okay, but this is nullable. So premature death equals frog lane equals null, then nothing else that dot value, except this returns me a death result. So let's say death result dot survive. Okay. So if premature death is not equal to survive, then result dot death result equals premature death, return result, do that. Does that sound like it might be correct? I kind of don't want to have to do this inside of the loop. I kind of want to do it after the loop, but before the instruction executes. You know what I mean? No, I think I need to run it. I think I do need to do that. So let's start again. So at the beginning of this function, we're looking at time 0. So this will calculate where the frog is. It will calculate the lane it is in, and then it will determine if it is dead at time 0. Okay. Then no. See you around, bagels. So we check whether it survives, because okay, so this moves forward 1 time unit. So okay, now I've convinced myself I want it up here. So this moves forward 1 time unit, and then potentially executes the program, the next program instruction. No, and then again, it will only check this. Oh gosh. And also I haven't determined FRG lane here. Okay, let me think about this really clearly. Okay, so the program starts at time 0. The first instruction will occur at time 1. So my logic when I wrote this was that this will execute the first instruction, and then the next iteration of this loop will check whether the frog is now getting hit in its new position, which means that it does not check its previous position. Sorry, I didn't mean this part. What checks if the frog is dead is, of course, this part here at the bottom after executing all of the instructions. So I need to check it before it executes an instruction, but at the time when the instruction would be executed, which is IP plus 1. So I need to do IP plus 1 here with the previous position of frog X. Yes, this is correct. And this is also the previous frog lane that we were in. Yes. Okay. I think I'm happy with this. I think I've convinced myself that this is correct. So let's find that same line in this piece of code here, which is here. Put that there, and then see if we now get a different result. It should say roadkill. It does say roadkill. Perfect. Okay, so I think I have now properly taken care of this. Why did you shorten frog lane to frugal lane? The benefit of that is that I'm assuming that I had another variable called frog lane somewhere else, probably down here. Yes, there you go. See, this used to say var frog lane. So you're probably correct that because that doesn't exist anymore, I can change that. But yes, that would have been the reason at the time. Okay, so now let's run this again. It's a bit of a shame that I can't run the exact same module again with the exact same parameters, but I'm reasonably confident now, so I'm going to start doing a solve bomb just to see if lots of frogs doing lots of moves. Yeah, you can barely see what's going on because there's too many going on at once, but there you go, they all worked and the bomb is diffused. Okay, I'm going to do that one more time. Why are they iterated one after the other, not at the same time? Because the first thing that the autosolver does is run the algorithm to find the program, and then it enters the program with repeated button presses, right? And then only after it has entered the program does it press the submit button or the start button, and then the next module gets a chance to run the algorithm. Not one, solve bomb. Or maybe I should, maybe I should do them in order so that I can actually see what's going on. And I can tell if the situation that we just solved for is relevant. Okay. Bingo. Okay, that's that. 3. Lots of oncoming traffic here. It's super slow. That was a pretty long program. I'm not convinced that that wasn't possible shorter. Okay, let's try number 8 here. We don't need to do them in order, do we? Again, the bottom one is super slow. Of course, the speeds are going to be the same in every module, but which one is the lorry might not be the same. I haven't been paying too much attention, but I think each one finds a solution, presses the submit button, and only then does it move on. Yes, exactly. That is exactly it. That is what I said. Solve. Those are some very small logs, and yet they were right the right position. Why can't it multi-thread? It's not that it can't, it's that it doesn't. Unity does not use multi-threading. Okay, I think I'm reasonably convinced now that this is working. It's not running into cars that are too close. Bingo. Okay, now I'm going to make a few changes. First of all, instead of going left, right, I think I am going to prioritize idling. I'm also going to remove this debug logging that I don't need anymore. So let's just remove that and that. File.write, let's remove that. So when it decides what instruction to put next, I'm gonna put idle as the first one, and then up as the next, and then left and right, and then down as the last option. Yeah, I don't think that's gonna make a huge difference. Oh, there was a lot of idling at the start. Why would it do so much idling? Oh my goodness. It solved the module and still put the frog in the wrong place. Oh boy, that is an entirely different bug. That, oof. Do I care? What do you mean, there it is? Yeah, Goofy, ideally it shouldn't take multiple seconds to find the solution. So of course I'm going to try to optimize this, but for now, let me just make sure that it's correct first. Now, do I care about this? I think I do. So, okay, let's remove this. I don't need that anymore. I can inline this, but that's irrelevant. So, let's see where it sets the sprite. What is it called? What was the function? Setup sprites, that's what it's called. So in each lane, ooh. Ah, okay, I can use null propagation here, that is helpful. Okay, so let's see. Right, okay, so it blindly sets the frog position to whatever this function is given. Right, so when we do this, we are just giving it frog x and frog y, which is the same as here, except okay, I know what's happening here, because there is this place in check program where it there we go, this one here, this is the problem. So this condition here checks whether or not you have correctly solved it. So if your frog, let's close that. If your frog is in position 0, 1, 2, 3, 4, 5, then in position 0, it's dead, right? But then 5 becomes acceptable all the way up to 15, right? And then starting at 16, it's dead again, all the way up to 24. And then with 25, it is fine again. Right, so that means this thing here, so we add 5, which would turn this into 5, 6, 7, 8, 9, 10, 20, 21, 29, and 30. Right, and then we divide that by 10 and then multiply by 10. That's the same as removing the last digit. But you can see that for something like 20, right, we still want it to become 1 rather than 2. We want this entire range of 10 to 20 to be allowed. So, I think I'm going to cheat because if I do this, right, then this will give me 1 for this value, 2 for this value, and then 3 for this value. So we know that if this is now an even number, then it is Welcome, Kilo Cloud. So if it's an even number, then it's exactly one of those corner cases. So I'm just going to subtract the temp x modulo. No, if it's even, I want to subtract 1 if it's even. Right, okay, fine. I'll just write it like this. If temp x modulo 2 equals 0, temp x minus minus. Right, and then here we just say temp x times 10. Okay, so I think I want to put a comment here. We want to allow x coordinates from 5 to 15 to all count as valid. This formula turns 5 to 14 into 1, but 15 becomes 2. Comma. So if the result was even, subtract 1. Subtract 1 to obtain the position of the goal we actually reached. There you go. Okay. Whoops, wrong button again. Timwe, kilobytes, lol. I don't blame you for not recognizing my tweet. I figured that it would be you. I mean, Kilo. I don't know any other people who call themselves Kilo, but I decided to call you Kilo Cloud because that's what it says. So I fixed the sprite. Now we need to think about making the autosolver algorithm more efficient. And I think one obvious way to do that would be to run it once only up to the point where the frog reaches the middle strip. And then once it has reached it, you don't need to care about the cars anymore. So I'm going to do that. I'm going to say if we ever reach, right, so here's an initial result. If that initial result dot frog y, let's do a boolean here. Var has reached middle strip equals false. Right. So if we have not reached the middle strip yet, but now the frog y is greater or equal to 0, 1, 2, 3, 4, 5. Is it going to be 5 or is it going to be 50? Let's quickly check that. Yes, it's times 10. It's times 10 everywhere, isn't it? So, yeah, we never divided by 10. So, go back here. Right, so if it's greater or equal to 50, then I'm going to say that we have reached the middle strip. And I'm going to clear the queue. And then queue dot in queue the program that we were at here. And then continue. So that will clear everything else from the queue. So it will try to reach the middle strip as quickly as possible and then go from there, I think. I suppose I don't actually need to say continue, and nor do I need, yeah, I can literally just queue.clear. And then this will add new things to the queue roundabout here, because when you're on the strip, you can always move left and right, so it will always in queue something. All right, let's try that. Okay, so let's see how fast it is now. All right, let's press this. Did you see how that was way faster? But then again, it's literally just going up, 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 up. There's only one idle in there. Okay, let's find one where it actually walks into a car. Bingo. That is much faster now. Awesome sauce. Okay, let's try something else where it's where it runs into a car. Here, let's say. That is number 4. Interesting, it started with an idle and then went right. Oh, that is very interesting. Okay. Right, one more for good measure? Or shall we solve an entire bomb now? How about that? Okay. So what it should do now is it should start entering program number 1, and then as soon as it starts that program, it will enter the commands for program number 2. Here we go. Yes. Alright, that was pretty cool. Okay, so I guess we're done. So let's quickly do the honors of submitting that. I don't need system.io anymore. I'm just gonna clean up this stuff here. Go back to this. And let's look through the entire diff. Okay, the audio clips thing, obviously that is for the test harness. So let's see what we've changed. Okay, that is just stuff. Most recent execute instruction. And then we've created this program. Okay, that is all of that. Here is the check program function. Yeah, that is quite different from what it used to be, I guess. Okay. All of that. Yeah, okay, and here's the comment I wrote last. Okay, so that seems fine. I don't think I've left any debug stuff in. Oh, I'm still not done. This is the entire algorithm. I haven't even scrolled past that yet. I suppose this will now never happen. I hope that this will now never happen. In fact, no, this can never happen because we have our allowed downs. So by the time it gets to 20 allowed downs, people will have stopped waiting for it because it will take years. So, you know, the game will freeze and oh boy, the game will freeze. Okay, you know what? I don't want the game to freeze under any possible circumstance. So I am going to change it to 2. Right, so if you genuinely can't find any way oh wait, this should be up here. There you go. If you genuinely can't find any way to solve it with 2 downs, then it's unsolvable. I think we can safely assume that. And when that is the case, we actually do want it to throw an exception. Yeah, and then the autosolver will just mark it as solved because of the exception. All right, cool. So let's go back to the code and yeah, let's just do that. And I think we're done. So add TP autosolver, push that. Ooh, I didn't realize that there were other changes. So let's do a fetch and see what Quinn has done. Update license, interesting. Oh, of course, that makes sense. Okay, so that was copied from Braille, which makes sense. That explains why that said 2017. Okay, so I wish to rebase my current changes on top of that. Why do I have unstaged changes all of a sudden? Okay, let's abort the rebase. I see. Okay, this sometimes happens. Oh, it's back to normal. Huh? Okay. And the rebase succeeded. Okay. Oh, no, it didn't. Okay, so let's try that again. Rebase. Yes. I think I know what happened. I'm going to push this first before... because what happened, I bet, is that something in the mod kit got deleted. Namely these files. I need to reinstate all these files, right? And so what happened is while doing the rebase, Git decided, oh, that folder there, right? And somehow the directory junction got removed, and then Git noticed all of these files as missing, and it saw that as as uncommitted changes in the workspace. But then when I aborted the rebase, it reinstated those files, but not the directory junction. So I need to go here and run my little batch file again, and that will that will restore those directory junctions. Okay, so thank you for watching, and see you all. Goodbye.